morning, everyone. It's great to be here. It's great to be in the presence of so many luminaries and so many wonderful professionals in our space. I'm humbled to be here. Many of you have started this journey in the industrial NDT and manufacturing space decades before me. But what I'd like to bring to the table is a slightly different perspective on what does it take to commercialize something, these technologies, and be successful. And with that, let me jump right into it. First, with a brief history of Varian and Varix, but before I go there, I was being asked, so you go from DR to CT to where? I think it all ends up in the cloud. So let's just get that out of the way. So Varian Medical Systems has a long history of being in the X-ray space. Only recently, Varian decided to carve out the imaging part of Varian into a separate company, so that's what Varix Imaging is about. Reality is Varix Imaging has been around for the last 40 plus years and developing X-ray based technologies for a very, very long time. And the company's essentially, mostly the center of gravity of the company is in Salt Lake City, but located globally with about 1,900 employees all over the world. And at this point, we're really looking forward to being a public company and growing the company. The company is mostly focused on the medical side. The origin of the company was in medical, but over the last 20 years, we've made quite a bit of progress, inroads into industrial, but it has largely been the byproduct of taking some of the medical technologies and applying it to industrial. Now, on one hand, it seems that way, but you'll see that quite a bit of the work that we've done actually, some of it started in the industrial space, and then we're supported back also into the medical space. And as I sit here and listen to the discussions about what it's going to take to make sensor-based non-destructive monitoring to be a success, I think about that. There's so much of that can be applied to the medical space. And there's examples that come to my mind I'll try to bring out as we talk about where things are headed with imaging. On the industrial side, our businesses are primarily focused on creating components for applications in both the non-destructive testing and the security side. And in addition to non-destructive testing, a significant part of our components go into the analysis space, so in the XRF, XRD type of applications. So today we'll talk about some of the testing and testing-related applications. The way you should think about our business is there are four technology competencies that we have. One, around X-ray sources, a variety of X-ray sources. We make about 400 different kinds of X-ray sources, along many different energy levels and categories of products. Second, around detectors, a variety of different detector technologies, detection for different detection applications. Third, a number of connect and control products. These are components that tie detectors, generators, X-ray tubes together into what becomes an application. And lastly, and increasingly importantly, software. As I've been thinking about how to talk about where imaging is headed from film to digital radiography to CT, what I realized was it's not just about detectors. Yeah, film is a type of a detector, but in order to get the full value of the imaging and through that journey, what we're finding is the X-ray source and the detector go hand in hand. And increasingly, software is becoming a very, very important part of that whole value system and value process for getting the results that you need out of your matched X-ray source with the detector, and then the software becomes a big part of what controls it and gets you the results that you need. So with that, let me just jump right into it. If you look at the history of time, barely between the time when Röntgen designed the X-ray, first discovered X-rays and designed the first X-ray tube, it took only about 20 years for the first. Sorry, I gave away my. That's how you give away the punchline, right? All right. But in about 20 years, the first 100 kV X-ray tube was built. That's pretty amazing. I don't think that was for medical X-ray. I'm not sure what was going through the mind of the people that discovered that. And unfortunately, I'm not sure exactly who the inventors were there. But if you see what happened where NDT started, I would have said, back in 1913, someone had this idea. And then as it moved forward to 1941, you can see the progression started increasing of the degree of innovation in this space. And then as you move forward, of course, there's the Varian brothers. The Varian brothers introduced the linear accelerator. I had to do this, Vijay. I looked for a picture of you from 30 years ago, and I couldn't find one. But anyway, this will make its way into the hallways of Varian. Varian brothers are there, and you're going to be next to them. But the interesting thing is, one of the first products after Varian introduced a linear accelerator was an NDT, was an accelerator for an NDT application for rocket motors. This was a time when there was a tremendous amount of activity in the United States to go to the moon, to send someone into space. This was the beginning of how Linux started getting used for industrial applications. Now, over the years, even though it started early, the use of Linux has continued to grow, but it has gone more into the security space versus the Linux space. And we'll talk more about that. And then, of course, Vijay, you were one of the early pioneers, and you've spent 30 years in this space, so you've learned a tremendous amount. And it's a great pleasure to be here at your company and company of others. If you move forward and see what happened beyond that, now this is a bit self-serving. It's only about Varian and Verix and PerkinElmer. I'm sure if I took your experiences and put them in here, what we will find is that between 1950 and where we are today, the rate of change of this technology platform and the innovation has been enormous. And the adoption of these technologies has been growing very, very rapidly, particularly over the last 10 years. So let's move forward and look at that. So as you look at the transition that's occurring from analog to digital, here's the good news. The good news is that it's moving forward, it's happening, and the better news is that if you look at it purely from a business perspective, fast forward to 2022, what's surprising is that there would still be about $500 million worth of film and CR being consumed annually. So the annual spend on film and CR in this space at the end of 2022 is still expected to be very, very high. Now that's because the adoption is growing, so the whole market segment is lifting up. But at the same time, CR and film are not going away as fast. And while you're seeing a tremendous growth in DR and CT-based technologies, clearly you see DR is 18% compound annual growth rate, and CT is growing at a pretty fast pace as well. The good news is if you are in this space and you're thinking of investing, even if you fast forward up to 2022, you've got a very, very long runway of adoption of new technologies. Not only that, for all the last 20 years, all the sites that have used film at some point going to convert from analog to digital. So the combined opportunity is pretty significant in this space. So this is the right time to invest in DR technologies that will enhance the imaging experience and the conversion from film to DR. So the second observation that we make here is that while DR is growing, CT is increasing its role as the modality of choice. As we find the movement from analog to digital, it's becoming obvious that DR has there's certain places where DR has applicability, but if you move in towards, if the direction is to move towards the more complex analytics and the more complex value propositions, CT plays a significant role, and that's why we're seeing the number of CT applications continue to grow pretty substantially. There are certain hurdles. I hear a lot of excuses about why we're not ready to put in an imaging system even in our factory. But I look at those and I go, those have less to do with technology. The technology is here. If you look at the DR-based systems, what's holding us back has been historically the fact that there's been a legacy, generations of people using film, the standards that go with it, the systems and processes that are set up, that are entrenched in the organizations. Those are starting to move out, but let's not underestimate how difficult it is to overhaul an environment that's been in place for the last 40, 50 years. All of the other issues, I see those more as non-issues. Initial cost, yes, it's high, but if you think about the total cost of ownership, and increasingly people are thinking about that objection's going away. Companies like us are becoming more and more open to different business models, so that initial cost of implementing imaging systems in your factories, whether it's in the factory or out in the field, ought to be going away. There are other technology issues around resolution, radiation hardness, ruggedness, etc. I don't think those are issues anymore, and I'd love to get your feedback. I think resolution on the detector side can be as granular as it needs to be. We heard from Professor Hanke, it can even go down to the nanometer segment level of resolutions. Okay, at that level there may be a cost issue, but in general, if you're looking to image below 100 microns, You know, we have 83 micron detectors, we have 76 micron detectors. How much more do you need? We think it's less about that. There may be still a challenge on the source side to try to get the right focal spot size to get there, and then electronics challenges on how fast you acquire. But just by itself, resolution itself we don't think is a hurdle anymore. And the last item that we hear constantly is, well, we don't have flexible detectors, that's why we can't change the way we scan pipelines. That's okay, if you take that on face value and say, okay, that may be true. The reality is the technologies are available for flexible detectors. However, they're not cost justified. It would cost us somewhere between $30 and $50 million to bring a flex product to market. Well, we'd have to sell about $500 million worth of flex detectors in order to get our money back, right? So the cost justification isn't there. And so we're trying to understand what would it really take do people truly want to bend a detector, or is there something else? Is this a proxy for weight? Is it a proxy for something else? Is there a way for us to achieve the same thing in a different way? Today, it sounds like people like wrapping film around objects, but let's think about how we do it in a different way that's commercially viable. So I think I see that as the only thing that we can't easily achieve today, but the rest seems like they're achievable. So the future is probably already here. You know, this journey started sometime back with DR, and we see the velocity of adoption increasing. There's been always a lot of complaint about form factor. One of the things that gets in the way is the form factor. We only have so much space to put in the detector and the rest of the assembly that goes with it. I think that's true. People are looking for cassette sized. We can now fold back in the electronics so that you don't have to spread them out and make a really big detector. However, the weight is still an issue. And there's still more work to be done to optimize that weight. Perhaps we can take a little bit more out by becoming more and more fine-tuning the design of the shielding. So there are software packages that we have that we sell externally, but we're also using internally now to figure out how to take out every pound of weight that we can out of the shielding. But regardless of whether it's a 320 kV application or a 450 kV application, which seem like these are very typical, size and weight seem to be, portability seems to be the main issue, but we're not yet 100% sure how much it's getting in the way of adoption versus the standards and the ingrained factory-based processes. I'd love to hear your feedback on that, perhaps your thoughts on what is really getting in the way. If you move this forward, so yes, size, form factor matters, resolution matters, there's spatial resolution, and then there's contrast. Spatial resolution we can deal with the detector side and on the source side. What we're finding is contrast and the image quality improvements can all be made through the right software algorithms, depending on whether you're taking the images for detecting something or measuring something, how granular do you need to be, how well those software algorithms need to be performed. We're pleasantly surprised by the degree, the amount of ingenuity that's out there in developing algorithms and software for image cleanup and image processing. And it does make a difference. If you look on the left-hand side of that circuit board, and if you look at this, this object, this connectors versus here, it may not be as apparent in this, in this big picture, but the resolution difference is pretty stark, and it's all done through software. So that's what's in the lab, in the factory. If you take it out in the field, there's a different set of challenges. In the field, it's more about the communication, wireless, and there's some other features like auto-detect capabilities that's needed. As you go on through this and try to understand what is it that would enhance someone's ability to make the field-based imaging to go from film to digital, frankly, when I look at it, the only thing that stands out for me is the cloud-based storage and secured access. Maybe the vendors aren't as far along as they need to be in being able to offer these services or capabilities. The reliability of that connection when you're out in the middle of nowhere looking at a pipeline, how robust can you really make that? Other than that, what we're finding is the detectors are there. Okay, if you get past the rigidity and the flexibility, but for most applications, we're finding that portability, it doesn't have to be out in the field, but if it's a portable detector that's being used in the factory setting, in a confined setting, in a controlled setting, we think it's there. We think the detectors can be applied very, very effectively. The wireless technologies are, the bandwidth and the speed of the new wireless standards are increasingly making it easier to transfer images. So we're not seeing much of a holdup from a technology perspective in the man-portable space. But then as we look at the detector side, we see a bigger challenge on the source side. Really, maybe where our focus needs to be is on the source side. If you look at the historical radiation-based sources, they're very convenient. You can position them very easily at the mouth of very close to your object. You can snake their way through systems. You get the argument of low cost, low initial cost, and ability to get into tight spaces. The downside of those are there's increased regulatory scrutiny, but despite that, there are about 8,000 iridium-based systems out there. There's probably another 5,000 to 6,000 cobalt-based systems. So there's a tremendous amount of radiation-based sources still being used. The LINACs, on the other hand, are getting closer to what these radiation-based sources can achieve through size and portability, but still not quite there. This might be a 20-pound source. The LINAC is still, you're talking about a 200-pound source. Yes, it can be carried around, but it takes 2 people. It's not quite there yet. So the conundrum here is, what has to happen to get away from X-ray-based sources, radiation-based sources to X-ray-based sources, tubes, and LINACs? And the benefit from that is you get much better imaging, right? So if you look at an example here, again, I apologize, the granularity isn't there, but you take our word for it. Here's an example of 100 millimeters of steel. These are the specs. This is what was achieved through a LINAC-based system, a 5.8 minute exposure. All 4 image quality indicators are visible through the LINAC-based test. If you look at a Cobalt-based test, it took 45 minutes, and only 1 IQI is discernible. So if this is the difference in the imaging outcome with the Cobalt or let's say an iridium-based source versus a LINAC, is this enough to move people over? We're not quite sure yet. It seems like people would rather put up with 45 minutes and a regulatory hassle versus putting in a LINAC. And so the question is, why is that? The only thing I can think of is the upfront cost and the portability of the LINAC or the tube-based systems. And so our focus has been on miniaturization, size, footprint, and the cost can obviously be addressed with a business model change. We're working our way through that. And then the discussion about flex, we talked about that. Here's a typical application, the way the film is wrapped around and images are taken. We've seen organizations create a variety of different robotics and structures to move the detector and the source. Those are doable. You can also use software to correct the images and adjust the image itself. I don't think we're going to see this in a hurry. We have made detectors in-house. We have flexible substrates, and the detectors are okay, but quality could improve, but we're just not commercializing them, and there's no real plan at all to commercialize flexible detectors. And we're not seeing anyone in the market either right after it. We've approached companies like Samsung, LG, and others to see if they would work with us to see, they have interest. They are interested in getting into the medical space. They want to make detectors for us, give us substrates and TFTs. But they stop when we answer one question, which is they typically ask us, how many millions of units do you want? And we say the whole market's about 30,000 units. And then they tell us that 30,000 is about 15 minutes of their factory runtime. And so then the whole economics just crashes to the floor. That's why those guys haven't been in this space. They have not come out with products themselves because they just can't justify the economics. So something to think about. Maybe we will remain in a space where there's a lot of film used, and gradually we believe it'll move over once the technologies start to shrink, start to become lighter, become more portable. The value proposition will be sufficient to move people over to the pipeline inspections over to digital technologies. So moving forward, I was talking to a radiologist friend in India. I grew up with him, and I was telling him about, he asked me what I was working on. I said, we're working on some iterative reconstruction algorithms for CBCT. And he's like, interesting. He sent me back this cartoon, and he said, look, your iterative reconstruction should have solved this problem, of the blind men with an elephant. And I was thinking about that. That's interesting. It's a funny analogy. But I thought that, geez, there's many things that we're trying to do here today that seems we're putting a lot of focus on the X-ray tube and the sources. But the reality is software can help solve many of those problems. And that got me going in the direction of software. So we acquired a company called Mevis. And Mevis came out of Fraunhofer. There was Mevis was spun out from Fraunhofer at one point as a Fraunhofer Mevis, and then it became a separate company. They're focused on image processing, image analysis, creating imaging components that other manufacturers use. But as we move forward, increasingly, the thrust appears to be that the software capabilities have to grow faster in order for us to make any more improvement in the detection technologies. Because we can build hardware, but there's still need for finding ways to tie the components together and finding ways to optimize the output of that hardware. So back to one of the comments Professor Hanke made, which is you want to bring the analysis as close to the sensor as possible. That is precisely what we've been thinking about, which is, I'll give you a medical example. We use computer-aided detection algorithms, CAD algorithms, to detect breast cancer. Breast cancer starts with very, very fine artifacts, very fine micron-sized artifacts. And all we have is post-processed, or this is done through post-processing, and at that point, all we have is structural information. We can compare the structure of the vascular structures in there, the muscular structures, and say, that looks odd. There is something there. So we can see that there is something. We can't tell what it is. Now, I asked our Mevis team, I said, hey, it would be great. Today what happens is a woman goes in, gets a mammogram, and then they tell her, we found something. Sorry, we can't tell you what it is. You may have cancer, but we won't know for another 10 days. Come back in 10 days for a pathology. Those are the 10 most miserable days in the life of that person. What if we could do it right at the spot and tell them, no, it's nothing, it's just a blood clot, or it's a lymph clot, it's okay, right? But what would it take to do that? To do that, the team tells me we're going to have to get closer and closer to the sensor. We don't have energy discrimination information. We don't have dose information. We don't have several other things that we could potentially get if the tube and the source, X-ray source and the detector could tell us a few more things. So that got us thinking about, we've got to get closer to the tube, we've got to get closer to the detector. And so that's our journey. So we've been thinking about what happens if we put a full-blown PC processor inside a detector. Our detectors have powerful electronics. We can put in memory. We can put in a terabyte of memory if you want. We can put in the most recent PC card. It doesn't cost us that much. What good would that do? Could we do better? And that's where we feel that's the direction we're headed in, saying we've got to put more capabilities on the detector so that you can put in your favorite algorithms, image processing algorithms on the detector, so the output of the detector would also be faster. You don't have to worry about acquisition. The detector is already acquired. Asynchronously, you can transfer the images out, put it into the cloud, break up the workflow. Break up the workflow so that the detection workflow, the diagnostic, the reading workflow is separated out. So we're thinking along these lines to see how we can improve the adoption of these technologies. It's not going to be about giving you a detector that's faster or a detector that has higher resolution. That might help. But for us all to see the benefits of 90% plus adoption of these technologies, we believe we're going to have to move in this direction. The requirements and the restrictions we know clearly. We can't make it bigger and heavier, and we can't make it more expensive. I think that we can handle that. It has to be tough, like a tough book. Yes, we can. By the way, if you ever go to a hospital and see how they handle the detectors, I've seen nurses throw the detectors to put it on the table and say, that's a $30,000 detector, don't do that. People don't throw $1,000 laptops, but they throw $30,000 detectors. It must have adequate battery life. This will be a constraint, battery and heat generation. We can control the heat. We need to find better batteries for adequate field-based use. And I think we can solve the battery problem. We can solve the wireless communication problems. Those are not real technical hurdles. The real challenge is the last item. We've been told several times that you do this, that's great, but how do we then handle all the workflow and change our environment to deal with this? People are talking about putting CT scanners for handbag scanning at airports, so that you can carry your laptops on board. It's not going fast enough. And the reason it's not going fast enough is the untold truth is TSA doesn't know what to do once that system is put in. because it's going to find more things. Then what do? You're going to back up the whole line? The airport's going to shut down? How do you handle that? Until they figure out how the workflow is going to be changed to accommodate this, TSA is probably not going to adopt these systems. But similarly, what we're finding is that these technologies, for us to be very, very successful with them, we have to come to the table with a workflow solution as well. So then moving forward, 100% inspection. It seems like, it reminds me of a Calvin and Hobbes comic strip that I saw. These are, for international folks who haven't seen them, they're cartoon strips that you find in newspapers here. Calvin's putting up a lemonade stand, and it says, "Swift kick in the butt for $1. But the sales are 0. He says, I don't get it. I have something that everyone needs, but no one's buying. So the real issue here is that we have these technologies. What will it take to adopt it? There are years and years of quality systems, quality processes in place, and they're just not changing in a hurry. Let me get through this, some of these. So if you look at motivations, there are plenty of motivations. We know that putting inline CT for 100% inspection will yield good results. Yet the challenge is that inspection needs to keep up with production. Now, in a manual environment, it does not keep up with production. But that standard is different. Once you put in digital standards, the bar gets raised and it has to keep up with production. And then there are sampling plans, quality plans, workflow implications. But if you have to deal with the first issue seems to be the real challenge, which is, can we get the right throughput? My answer is yes, we can get the right throughput. That may not be the real challenge. The real challenge still might be that we still have to solve the issue of legacy factory environments, cost we can deal with, and software has to continue to get better for automated detection. So the question of, are we there? Is adoption going to happen or not? I think adoption is going to take a lot longer until we figure out how to be able to retrofit this into legacy environments. I've got a few examples, and I'll skip through these really quickly. If you look at a typical CT type of an object that needs to be scanned, a 225 kV system will do an adequate job. And it can. If the spec is to have a throughput in less than 60 seconds, it's absolutely achievable with the right resolution. If you want to improve that, then two things need to happen. We have tube technologies that will give you a very small focal spot, 3-4 times the power, and much, much greater dose. Well, that won't be enough. To do that, the amount of volume of data that you're going to generate will make the detection side of it slow down to a point where it won't be useful. To do that, we have to improve the detector side. So there are IGZO, it's indium gallium zinc oxide-based detectors that we've tried. They work very well. They're good detectors. We're testing out the rad hardness of those. But we could increase imaging speed 2x or more, and with a higher resolution. And if you wanted to get greater speed, you could, or if you want to slow it down, you could. And there are trade-offs. So the detection technologies are available. The source technologies are available. We could improve the speed. So then what will it take to get to 100% inline scanning? Not clear yet. One thing we do know for sure, that software algorithms have to improve so that we can do automated defect recognition, or computer-aided diagnostics as we call it. So if we can improve the software, we can do 100% CAD, we can get the red, yellow, green outcomes for quality. If we can marry that with a good workflow, then I have no doubt in my mind that we will be able to get to 100% inline inspection. Same thing can be said about mega voltage imaging. Linacs can be used for NDT, for high energy systems. The challenge there is slightly different. Now you're talking about getting 30, 40, 100,000 rads per minute type of dose. How do you deal with that and the volume and the speed? There we believe even though standard detectors work, our impressions are that we'd have to go to some form of strip detectors to really speed up and make it effective. With that kind of volume coming out, you need much higher efficiency simulators to make it work. The traditional Gadox and cesium are not going to cut it. I think it's cadmium tungstate type of simulators, higher efficiency simulators with smaller detectors, with smaller packages so the data can be moved off those quickly. So those are the directions we're headed in, and we think we can use these technologies then to drive adoption. The bottom line for us, the future started. All the technologies we were talking about all started in development many, many years ago. It's not clear at this point that we have reached a technology boundary that's preventing us from getting there. What's preventing us from getting there, we believe, have more to do with the workflow. My hats off to companies like Volume Graphics that are helping in this regard. Volume Graphics has terrific software applications for handling enterprise workflow so that we can automate the whole process from visualization to getting the red, yellow, green at the end of it. That's what's needed in order to make this thing happen. So I know it's a strong statement, but we're seeing that, we're feeling that, and I would love to have this debate with you. We think the future is here. We think all these technologies are here. There's a little bit more work to be done. Some areas where the technologies are available, the commercial feasibility may not be there yet, but we believe this is a very positive and exciting time for us. We believe that the future that Professor Hanke painted is very plausible and very doable. Thank you.